the fine detail about orienting parts in the chamber. And so it's relative. Basically, the approach that we take is for the part, we define sort of what the center of the part is, and it could be, it could be perhaps. I mean, we can find the center of the part as the center of gravity, but more simply, we can simply define it as the center of the bounding box, of course, right? And to go that way. But effectively, we have the center of the part. We have our coordinate system here, x, y, z, and so the sort of the starting point for the orienting of parts is to orient the center of the part. So, for example, this part here, and again, it's just the x, y, z coordinates of the center of the part that we would mention. So, this part here, this is for a part that is, we have sort of 180, maybe 200 millimeters square build form. So this part would be in a positive x direction of about 90 millimeters, a positive y direction of about 90 millimeters. And if this part is 100 millimeters across, the center of it would be at 50. So we would have this coordinate 90, 90, 50 for the location for this part located here. And without saying anything else, we can say that it's a vertical part, and that would be sufficient to describe it. And again, you can see that we have different combinations of plus and minus signs, but for all of these parts, the center is at a z value of 50, so the third number is for all of these is 50. So now the question is well, what if this part, these parts are not straight up and down, what if they're rotated in some way? And in that case, what we do is we have to add to the coordinates, the x, y, z coordination point, we have to add to that some angular measures to describe the rotation of the part. And that, in this case, we have an ABC orientation where, again, this is listed in degrees. I suppose it could be radians just as well. But the positive is shown here, where the direction of rotation would be this way is positive. The rotation around the x-axis we call plus A. The rotation, again, sort of in this clockwise way around the y-axis is the plus B direction, and the rotation in this direction around the z-axis is plus C. So we actually could describe, in this case, the rotations by using the example, by this angular orientation or description. However, when you have to appreciate that when I rotate the sample, it changes the location of the center of the part, and so that it'll have an impact on x, y, and z if I rotate the sample. We see that here with these locations where suddenly we start to get these oddball numerical associations. It kind of has to do with the fact that I'm actually rotating the part, which changes, and I'm not rotating about the center of the part, so it changes the location. All of these are at y equals plus 90, so that part didn't change. These are all at negative 90 on y. And so that's the way we go. So in this case, this shows the rotation of B and not the B axis, and rotating around the y-axis of minus 45 degrees. Then these in front here are rotated at B equal plus 45 degrees. So basically what we need to describe the location of the part is effectively the location of the center of the part, the center of the bounding box, and the angle of rotation. So we can, in this case, the parts that I showed, I think I can gloss over this, but basically what we do is for those 6 samples, we would list the location and the orientation of the part to describe it. Okay, so that's the really complicated version. It turns out that for most parts, the geometry is such that we can sort of simplify the notation of the orientation of the part. And I show this for parts that basically have sort of a cuboid kind of look to them. then we can refer to the bounding box, which is always a cuboid, and we can describe the orientation of the part, at least maybe if not its actual location in the building. We can do that easily enough with the coordinates, but the rotation of the part in the chamber, if in fact it's built in a way where the bounding boxes, these cuboids, are sort of parallel to our coordinate system, which is often this is the case. We can define the orientation by the three letters. The way that this one works is with the orientation, I have three directions on my box. What we do is the first letter here is associated with the direction of the longest length of the three lengths associated with the cuboid. So here in this case I have a long length parallel to Z. The second longest length is parallel to X, and then the shortest length is parallel to Y. So we simply list the directions in decreasing order based on the length of the bounding box or the part. So we can call, we would call this, this would be an X, Y, Z part. You see how this works, right? So we can describe the orientation this way. So that's one simplification. There's another obvious simplification that we can do is, and typically we will do this, for rectangular type shaped parts, because the third letter is completely redundant, we can drop the third letter because there's no value in adding it, right? So what we can do is we can call this an XY part, call this a YX part, this would be a ZX and a ZY part. And again, my experience is when I sort of look at the literature and how people refer to parts, this two-letter designation is not uncommon. I see this. I don't see too much of the coordinate system where you have the coordinates of the center of the part and the angular rotations. I don't see that. I don't know if I've seen that anywhere, to be honest with you. But I see the two-letter nomenclature quite a bit. So, for example, we can extend it even further. This gives an example. If I have something that has a length and a width, we can use this two-letter orientation if, in fact, it's oriented sort of in an up, or left, right, or forward, backward orientation. And for samples that have some degree of symmetry with a single long axis, we can simply drop the second letter and simply refer to the long direction of the part. And this is extremely common, where we would talk about, for example, maybe you've seen this yourself or used it, say for tension samples, whether it's a dog bone or a cylindrical sample, we talk about that it's a Z sample or an X sample or a Y sample. Z being really popular, right? So we talk about a Z direction bill or maybe an N plane bill, which would be say X or Y or something in between. So anyway, the specimen, there's some other, everything that I've mentioned, if you want to find it, here's the number. It's ISO ASTM number 52921, standard terminology for competitive manufacturing, coordinate systems and test methodologies. That's the standard that describes all the orientations. So with that, I think at the end of this, so thank you for letting me share that with you. And now we'll go on to part 2 here of the microstructure. And we'll talk about, continue to talk about defects. So, here we go. All right. So, let me check my schedule here to make sure. I think we go till 1:15, if I remember correctly. Yes. Okay, so we'll take a break. We'll take a break and maybe a half hour or so. So anyway, we're going to part 2 on microstructural and macroscopic defects. Here's the basic topics. What I want to talk about is these common defects that occur in additive manufactured parts in general, metals, and specifically in DED parts. All of the original work for the development of these PV diagrams was done with DED, for what it's worth. So we have feedstock porosity. This is basically porosity that exists in the feedstock and which continues during the processing and is manifested in the part. The classic example of this is, it was sort of an eye-opening experience about 10 years ago when a group, I guess it was Tony Rollett at Carnegie Mellon, was the first person that I saw present this work. It turns out that the powder, for whether it's for DED or for powder bed, the powder itself, because of the nature of the way it's manufactured, typically it's atomized. Powder is what we typically use in additive manufacturing. It turns out that powder actually has porosity in it, and some fraction of that porosity remains in the final part, maybe 10–20%. It turns out that that porosity has been in the powder all along, but the powder processing people don't care because they do all this sintering and pressing of the powder that sort of removes it. In this case, all we're doing is doing a quick melt and resolidification of the powder, and often there's not enough time for that porosity to escape, and so it's captured in the part. So that's what the feedstock porosity is. Lack of fusion, we'll talk about in great detail, but this is basically if I don't have enough energy to actually completely densify the part locally, we can get these fusion errors. We'll look at that in great detail. Gas porosity is typically associated with keyholing. That's some really nice movies to show you of that effect. So I'll postpone any word solution until then. And then there's also a volume phenomenon that happens. I've talked about this a little bit already. It happens at very large scan speeds at really almost any power setting. And it's associated with the fact that we wind up with a very long liquid stream that's the surface energy destabilizes that long column, and so it breaks up into little droplets on the surface of the build. And so these are all kind of captured in these power scan speed diagrams, PV diagrams. I already showed you one. We'll be looking at some more. But then we also these are the microstructural defects. We also have the macrostructural defects, some of which I've already talked about, like distortion, cracking, surface finish defects, and oxidation. So we'll look at those to some degree too. All right, so here we are back, and I've shown this already, the PV diagram, the laser power, or it could be electron beam power just as well, versus the scan speed of the beam. And we have these 4 areas typically of observation where if there's too little power, we can get the fusion errors. If there's too much power, too much energy done, we can get keyhole porosity. And it shows out here at the high scan speeds where the balling occurs. I drew this. This is really new to me. Nobody else does this, but because it really doesn't matter. But it turns out that the balling that happens out here is associated with this long melt stream, right, that destabilizes. It turns out that people have observed balling in here at extremely low powers, and this is a different mechanism, but it's still kind of balling feature that we have. The reason we don't care about it is because it's way below failure. It's sort of like if you're looking at a failure mode after another failure mode. It's like, who cares? It's already failed. So why do we need to explore this? But effectively what happens here is where there's enough laser power just to melt a little tiny bit of pool, and that pool will sort of ball up because there's nothing to restrain it. It'll ball up into a sphere and solidify. And then the laser beam or the energy source moves down a little further, that repeats that, and so you can produce this line of spheres, which is like a balling effect. But it's kind of a different mechanism from the Rayleigh stabilities that we have up here at high scan speeds. So anyway, but I mentioned that just in passing. You remember we had the energy density relationship here, and so sort of implicit in these PV diagrams is that the hatch spacing and the layer thickness is not varying. If we vary those, then it's sort of an apples and orange comparison. So one way to think of this is if you look at these boundaries, you know, these colored boundaries and this black boundary here, basically as I change the skin hatch spacing or the layer thickness, those lines are going to kind of move around on the page, right? But they still have the same form. So obviously, you know, you have to be careful in terms of using this. And again, you know, I guess I would acknowledge that for most work that I see, people are not messing with the hatch spacing or the layer thickness anyway. So it's you know, this is not a great sacrifice to be able to have all this constant. All right, so here's what some micrographs of what these various regions look like. You have to appreciate in this one that the Z direction is this way. So here are the layers. Here sort of going almost vertically. But what we have is there's just not enough power to completely densify and melt everything. So here's some of the feedstock powders. This is a powder-based micrograph. So there simply wasn't enough energy to melt everything. So we get these very large areas. This is quite exaggerated here, where there's a very large porosity, and we see these kinds of features. That's what we see down here in the fusion air region, is this type of structure. Up in the keyholing area, there are, it's quite different. We can distinguish these two quite easily, right? Up here, these are typically very spherical, various sizes, and there's quite a few of these. This is a 200 micron marker, so we're looking at maybe, you know, 15 layers here, and we see there's all kinds of porosity here. This is the keyholing effect. I'll show you again. I'll show you some how this porosity forms in a little bit. The third area is the balling effect. So this shows an example in a nickel-based alloy from Colostro. He was at Catholic University of Belgium years ago. This is quite an known plot. So this is looking at the XY plane. The laser being scanned along here, and you see that we form these little spheres. The spheres are critically the diameter of the beam size, you know, not surprisingly. And I would mention as well, sort of maybe if out of vanity and nothing else, that the term balling was actually a term that I coined back in 1990 from this paper. It was in the SFF conference proceedings. It was the very first meeting. And so we were working with metal powders at the time, and so this is what we had observed as forming. So these, you know, this gross balling effect that we see here, and you know, you can read the quotes, but basically this was the first use of the term in additive manufacturing context. So I'm very happy about that. Okay, so here's some defects in directed energy deposition parts. So it shows what these might look like. Again, this is from the material handbook. ASM has an encyclopedic set of volumes, again, over 20, because this is number 24, on various topics related to materials. In volume 24, and there's actually a 24A now also. There's 2 volumes dealing with additive manufacturing. And so I recommend those as a general resource. Particularly if you have an interest in materials. I think that those volumes are actually very useful in general for anyone working in additives. And 24A is heavily emphasizing metals for what it's worth. So anyways, here we are. So this shows some of the effects. It shows the surface connected porosity up here. Lack of fusion, you know, appears like this. typically it's lack of fusion on the micrographs, shows up as these very large, irregularly shaped pores. And then they have these S-trap pores, which I interpret these to be probably the feedstock porosity. Because it doesn't really do this micrograph overall, those don't have the look of, first of all, it doesn't have the look of the keyhole porosity, but also if we're having fusion errors, you wouldn't expect to see keyhole porosity because they happen in different power settings. So this is most likely porosity that came in with the feedstock, which I assume it was powder. Okay. Okay. Here's the movie from of how keyhole forms, the keyhole porosity forms. So if you're familiar with laser welding or laser manufacturing, forming a keyhole is here. This shows a keyhole where the white space here is basically nothing. The light gray is molten metal. And then, of course, we have the parent metal is the dark area. What keyholing does, it's not always a bad thing. It is in additive manufacturing, but in laser manufacturing, it's not necessarily a bad thing. What keyholing is, the phenomenon is that the laser beam will strike the surface of a material. And if the beam is sufficiently energetic, what always can happen is we melt the metal. But with keyholing, what happens is the power is so high that the liquid is actually vaporized into a sort of a plasma. And what that does is the effect of that is that we get we call it a keyhole. It's a very deep transfer. Basically, the laser will interact energetically with the plasma, and the result of that is it increases the heat transfer scenario in a way that we can produce a really deep hole. And so for like laser drilling, keyholing is just a way of life. But what you see here is a very deep fusion zone that we get from keyhole. But we don't have porosity from keyholing normally, but we do with additive manufacturing. That's we have to make the following observation. I got these plots from Tony Wallett. He's at Carnegie Mellon in Pennsylvania, in the U.S. And what he did is he used a synchrotron where he basically put powder. I think he usually worked with titanium, Ti-64. He'd take titanium powder and load the chamber, the synchrotron chamber, and basically he would then have a laser scan the surface or do things at the surface, and you can sort of visualize what's going on. I'll show you, in this case, this is just a stationary laser shooting down into a powder bed, which we're going to see right here, hopefully, in this movie. So you can see the laser coming in, and what we see here, the white part is actually molten metal. So I think it'll run, hopefully it'll run again here. Maybe. It's not really, it's ready to see. So there's the laser, comes down, it creates that melt pool, and then when the laser goes off, you see there's some rebounding of the melt pool, and it makes a melt that solidifies up. Notice there's no porosity anywhere. Right? The issue is, it's going to occur when I show you this one. It has to do with the fact that in additive manufacturing, we're actually moving the laser. So what we do is we move the keyhole, and that moves the melt pool in a way that looks like this. So what we have, this shows the case where here's the laser beam coming down, and we create this big melt pool. Because the laser is moving from left to right, we have this melt pool that trails behind the laser. And if the laser keyholes, what happens is it creates the keyhole, as we will see, the bottom of the keyhole just flails around fairly indiscriminately. And occasionally, it'll sort of break off and it leaves some porosity in its way. That porosity down here at the bottom of the keyhole will sort of roll its way up the melt pool here. And if the solidification front crosses it before it can work its way out of the molten pool, then it's stuck in its keyhole porosity. So let me show you this. It's actually, I think, a fairly dramatic video here. So let's take a look at this. So here comes there's the laser. In this case, the light is actually the keyhole. So you see how it blocks off the porosity here, and which is the source of the keyhole porosity. And again, you know, obviously we can't see the laser, the solid solidification from coming through. But you can kind of imagine if you see one come off, that was pretty quick. See how that one rolled up? You know, it's sort of, you get this one right here, and I'll do it again. Watch this second one. You'll actually see it kind of roll up the solidification front, and then it freezes in place with the solidification front moves past it. So yeah, so watch that one. Yeah, so you can see how this goes. Again, this is still I-64, and you can see the other parameters here. Yeah, you can watch that porosity roll up. Yeah, the second one right here. See how it rolls up the solidification front, and then the solidification front passes and it freezes in place. So we think we have this fairly well understood. These are very round spherical particles. Yeah, of porosity. Yes. Yeah, this is porosity. Yeah, so the keyhole is the light material, kind of like a homicide, essentially. It's because that's what's floating off here to give the porosity. It's basically it's the keyhole part where there's no metal is popping off here. So these are all porosity. Yeah. I'm sorry? Yeah, sure. Oh, absolutely, yeah. Yeah, I'm not sure what that part is. On the stationary one, I don't know. Actually, I'm not sure what this back part here is either. I don't know if it's a perspective thing of the thickness of the sample.
The process is engaged.
Yeah.
After processing, speed has engaged the dark region.
Okay, so this is the waste region. So there's a build up from that as well. Yeah, so it could be that. Yeah, it very well could be.
It could be possible even laser also.
Yeah, I guess possibly could be. Yeah. Again, but I think again, I haven't done these experiments, but I think I'm pretty confident that what we're looking at here is porosity. Yeah.
Middle images are this CT scan images?
I'm sorry?
Middle images.
Oh, I'm sorry, where are we?
Next.
This one?
Yeah, these two.
Yeah, these two.
Next.
Yeah.
These two. Are these micrographs?
Oh, these? Yeah, I think these are just cross sections. I think I'm speculating that these, since they came from here, from Tony, that these are would be cross sections from the same state.
Yes. It's clearly visible the defects.
Yeah.
Right?
Here?
So
Yeah.
they are not micrographs, right?
Yeah, well, yeah, it's the size of the, yeah.
Yeah, the defects are clearly visible.
Yeah.
Are they macrographs or something?
Yeah, I think they would like a micrograph. But again, the keyhole, the laser source is, I forget what the laser beam size are, but it's pretty fine. Like,
And these defects are like these defects only?
No, it's not the case. Yeah, because these are both stationary. The porosity forms is intimately associated with the motion of the laser beam. Yes. Yeah, it's the moving. Yeah, if the laser beam's not moving, it doesn't generate porosity. It's the moving beam that causes the porosity to form. It's the bottom of the keyhole basically breaking off. At least that's the mechanism. That's what everyone said. So yeah, right. Yeah, we can talk more about that. I think if you have other ideas, certainly. An example of the fusion errors. This shows an example, I guess, from the keyhole porosity. You can see that they're fairly distinguishable. The two different values that we have here. So and again, there's this sweet spot in here where we can actually generate good parts. This shows a view from this region here. You can see it's quite dramatic. The quality. Again, these small pores could be feedstock porosity. Could be just a random void that forms. I mentioned to you yesterday, I believe, that actually these PV diagrams were produced based on density measurements, and so we want full density parts. But it turns out that it's possible to have a full density part that does not have full mechanical properties. And so there was a fairly large multiple university research effort that happened in the U.S. Maybe finished, I guess it was it after COVID? It may have finished after COVID. But involved with that was a guy named John Lewandowski, who's a professor at Case Western Reserve, who was part of that team. He was looking at mechanical properties of these parts, and what he determined is that it's possible to build a good part and still not have good mechanical properties. And further, he noticed that where the good mechanical properties were was actually up here on the high power side of the good parts section. So effectively, he determined that really if we want to have parts with good mechanicals, that it's not good enough just to be in this region, but rather we want to work up here at the highest power possible. Basically, we want the highest energy density possible that does not cause porosity, which means we want to be way up here. This is where the sweet spot becomes for performing mechanical properties, or for obtaining parts with good mechanicals. Okay, so with that, let me talk about some general guidelines then for metal additive manufacturing. This is general, but I'll try to emphasize the fusion part, which is what DED is. But basically, if we look at the various additive manufacturing classifications, remember there's 7 of them. Fiber jetting and sheet lamination are 2 technologies that can be used to do additive manufacturing of metals. And really, if we think about, what do we need, what does the feedstock need to possess? It turns out that really the main thing it needs is the feedstock just has to be in the right form to be processed. We don't have to worry about how the manufacturing goes, because we're simply going to glue it together with some second binder for these 2. So, however, for fusion processes, powder bed and directed energy deposition, what's been determined, just as a rule of thumb, is that if the metal will weld well or will cast well, then typically they can be processed well in additive manufacturing. And so when we look at the metal systems, and I show some here that can be processed well by additive, what we find is that they're also readily weldable and readily castable. And again, that's just a broad general rule. So, so let's look at some examples of this. Again, this is work that was done at Texas. It turns out that in the aluminum alloys, one of the common systems in additive manufacturing is the aluminum silicon tin mag. It's it's a 10% silicon alloy, and it turns out that if you look at its history, it's been used as a casting alloy for a long period of time. So it's natural that it would cross over. But it turns out that so it's 10% silicon, and the issue, one of the considerations is that if we cut the silicon down to about 0.5%, and with minor other adjustments to the composition, we wind up with an extremely popular raw aluminum alloy, which we call 6061. So it's this aluminum silicon mag alloy. It's probably of the structural aluminum alloys, if not the most popular, certainly one of the most popular. But the problem is when we run aluminum silicon tin mag that has 10% silicon in it, it runs in additive manufacturing beautifully. However, when we run 6061 aluminum in an additive manufacturing machine, where again the Z direction is vertical here, it turns out what we get is we get something that looks like this. And not only the dark feature on these on this micrograph is not a porosity. Those are actually cracks that have formed. So the material will crack, and then with each succeeding layer, the crack just sort of continues to go vertically upward and to extend through the build. So the part's just all cracked up. Again, the explanation is clearly a metallurgical one. If we look at a phase diagram for aluminum silicon, 6061 is down in this range with around 0.4 to 0.8% silicon. So we're now actually down in this range here. Whereas the aluminum silicon tin mag is actually, you would think it would be about here. It turns out it's actually a so-called protective composition. We don't see it on the binary diagram because when we add the magnesium, it shifts the diagram a little bit. But basically, for this system, if we plotted aluminum magnesium with this amount versus silicon, what we would see is that this 9 to 11% silicon would be right at the protective here. So what happens with this is sort of universally true of casting alloys, is effectively, if you just ask anybody, what would you pick for a casting alloy, the people who work in that area, it's like you pick a detective because it behaves like a pure element. That is, if I have liquid up here, I heat the material to form liquid. As I cool it, it comes down to the detecting temperature here, and I have a thermal arrest just like on an aluminum metal. And it sits at this thermal arrest at a single temperature until all of the liquid is converted to solid. And then it proceeds down here in the solid state to pull back to room temperature. And so that's the castable additive manufacturing beneficial material. However, if I go off eutectic over here and try and do the same thing, what happens is I'm in the liquid state. As I cool down, as I enter this two-phase region, where from this temperature down to this temperature, I have a mixture of liquid and solid. And as the solid forms, with the cooling temperature, there's shrinkage, and oftentimes these form with a sort of a polymer or a dendritic kind of array, where it's very easy for the liquid to get pinched off from the main body. And when that happens, with further cooling and contraction, we tend to form either porosity or cracks. Because the solid, as we go from liquid to solid, there's a lot of contraction that occurs. So typically, these off-view techniques, as we say, are typically not noted. They're noted for not being particularly manufacturable by casting or welding or by manufacturing. 6061 is it's a raw alloy. It's designed to be deformed into shape. It's if you look at the handbooks, it may list it as being weldable or it may not. And the issue with its weldability is the only way that it can be welded is they use special filler metals that are high in silicon. And the reason is obvious, is what it does is it increases the silicon in the metal region and tends to move the composition of the metal from over here so that we get good solidification. So 6061 historically has been weldable with high silicon electrodes or filler metal. And then I guess my final footnote on 6061, just to complicate things, is with the machines that we use, and that most people use, it's a total failure to produce 6061 additive manufactured parts. It turns out there's at least one machine that's available. It's a British company, Renishaw, produces additive manufacturing machines. And for some weird reason, they're actually able to successfully process 6061. I think I haven't heard a consistent reason for why that is. I think one of the distinctions is I think they have a much higher power beam, and so there may be something associated with maybe the pulley rates are high enough that we can avoid the nasty complications that happen with other machines. But anyway, I just mentioned that just as a further complication of how things work. Okay, we talked about there are other materials-related challenges associated with additive manufacturing of metals. One is that metals typically have an affinity for foreign matter, and it can be contaminants, it can be oxides, it can be, in this case, with titanium. We see on the left side, they show some titanium nitrides that are formed in the material. And these generally are all it's sort of the same story. What we have is we have the material, either the metal itself, the feedstock itself, either has elements or alloying elements or foreign matter that is in a distributed position. But when we melt and re-solidify during additive manufacturing, there's a redistribution of those elements or contaminants, and we can pick them up in a more macroscopic, measurable way. Again, titanium is somewhat unique because titanium can dissolve a lot of oxygen, and so if it dissolves a lot of oxygen during the processing, then during solidification, the oxygen will come out and we'll get titanium oxide formation in the material, which, again, may or may not be a good thing. Another issue, I guess, related to metal additive manufacturing is that metals typically have a high reflectivity and thermal conductivity, both of which make it harder to process. So the energy beam comes down. We talked about this earlier. The energy beam will tend to bounce off the surface of the metal, and we can get again, this shows the absorption coefficients, although there's not a y-axis to see what those are. But again, depending on the wavelength of the light, we get different absorptions, and what that results in is basically we just have poor coupling of the energy beam, in this case the laser beam, to the surface. One of the advantages of electron beam DED in our quality DED is you don't have to worry about those issues of coupling. But in all the cases, we do have to worry about thermal conductivity and with heat conduction, because what we would like, ideally, is we like the energy to form the melt pool and for it to flow a little bit to form the bulk its part. But if the thermal conductivity is high, the heat conducts away very quickly in the solid state, so we don't have that concentrated heat source as much as we would if we did. So thermal conductivity can have an effect as well on the challenges. So, for example, people have done that in the manufacturing of copper, for example, which is sort of the extreme case of high thermal conductivity, although aluminum is not far behind. And they can't be processed. It's not impossible. It just makes life harder for us. The third is the residual stress. We've already talked about that to some degree, so I don't think I need to belabor it here. But again, this is not something that we worry about very much with polymers, because the residual stress cannot be greater than the yield strength of the material. So if I have a material that has a yield strength of 10 or 15 megapascal, it just can't generate much residual stress. However, if I have a part that's got a 700 megapascal yield, like many of the metals we deal with in additive, I can create some pretty hefty residual stresses like we've seen. Okay, another issue to deal with is distortion. And we talked about distortion for residual stress, but I also want to talk about distortion from the perspective of just simply the various effects of processing on the shape of the part. So this is work that I did, I get 2008, that I think it's a good example of how the processing can impact the distortion and the distortion of the part. And this perhaps may be more directly applicable to metals in the indirect form, where we're doing, where we have binders that have to be burned off in post-processing steps, as opposed to with DED, we don't have maybe these exact steps involved in the post-processing. So with that caveat, let me just show you here what we found. This was what we did. All of these parts are it's called reaction bonded silicon carbide. The way the step works is this. Ceramics are extremely difficult to process in laser center, well, in additive manufacturing in general. And so what we did is we used what most people do. We used an indirect approach. So what we did is we took, in this case, silicon carbide powder, and we added a binder to it. So we mixed binder. The binder was an epoxy that we used. One of the features of epoxy is it's what's called a high ash material. That is, we used phenolic. It was phenolic. Phenolic is a high ash material. So what that means is when it burns, it leaves behind about 50% carbon if you completely dissociate it. So what we did is we mixed the silicon carbide with the phenolic. We put it in this case, a laser sintering machine, and we scanned it to create a part. And what happens is the phenolic is a thermoset material, so it will cross-link, but the time it was insufficient in the chamber for cross-linking to occur, so we simply melted and we solidified the phenolic. So our green part is basically silicon carbide particles glued together with phenolic, uncured. But then what we did, and we call that the green part. Then what we did is we basically, in some cases, we would infiltrate with an epoxy, through the epoxy, just so the part could hold shape when we get rid of when we process the phenolic. And so we would do maybe add epoxy, and then after that we would effectively heat the part up, remelt the phenolic, and give it enough temperature for it to cross-link and into a thermoset fashion. So once the phenolic was cross-linked, then we can heat it up to a high temperature, and we basically would burn off all of the polymer. But the phenolic, after being cross-linked, it doesn't melt. so it keeps the part from falling apart. And we're talking about 700 degrees centigrade or so, 800 degrees centigrade. The phenolic and the epoxy all burn off, but because it's a high action material, what it leaves behind is carbon. So now we have the silicon carbide that's held together by carbonates, which is what we call the brown state. And then what we would do, and this is standard practice for producing reaction bonded silicon carbide, is we would take that preform, it's a porous preform, we would heat it up to about 1750 centigrade, very high temperature, and then we would wick in molten silicon metal. So what we have at the end of the day is this is a framework of silicon carbide that also has silicon metal in it. And again, it's a standard commercial grade material, reaction bonded silicon carbide. And in whole shape. So that's what all these parts are. So the reason I mentioned that is this is a good example of sort of how the processing steps can impact the distortion. So what we did is we built cubes, which were easy to build. And then we actually measured the change in the dimension in the X, Y, and Z directions as the material goes through these various processing stages. So we start here. This is the percent change in the distortion in the, I would say, expansion or the contraction. It's the linear change in the dimension in percent. So this is 0, 10%, negative 8%. And so 0 is basically the solid model is the CAD. And what we did is as we built the green part, there are two sets of curves here. One is these solid squares here. The other of these curves here in between. And what these are is these lines were reflective of measurements in the X, Y, and Z direction. So what we see here basically is there's not a lot of change here in the direction, which means there's not a lot of anisotropic shrinkage or expansion as we process. And that's the linear strain distortion. It turns out that you can also calculate a volume strain, which turns out that if you have the principal strains, which is the case here, it turns out that the volume strain is just 3 times the linear strain. So basically, this is going to be 3 times this curve. So but anyways, having said all that, now we can go, I think, fairly quickly through this. What we have with the solid modeling, there's about a 2% expansion going to the green part. So the build part is expanding. As we go to with infiltrating with epoxy, we get some shrinkage. As we burn off the part, we get more shrinkage. So this is the brown part. And then on heating it up to the high temperature, 50, a slight expansion. So we heated it up and just pulled it back down to room temperature, did the measurements. And then finally, infiltrating with silicon results in very little dimensional change. And so it turns out it's sort of serendipitous that we start off at 0, we kind of end up at 0 after all this fluctuation in between. And so we sort of lucked down in that respect. So this shows on the bottom here, shows the percent volume change as we go through. And again, so it will, in the end, this is relative to the CAD model. So we expand when we build the part, when we shrink when we do the micro burn off. And so we have quite a bit of part that's in very good shape. So the point is that as we do the builds, regardless of what the additive manufacturing process is, and do the post-processing, we can get shrinkage and expansion that occurs, which may or may not have an impact on the quality of the part. Having said that, if we, which is the case for a lot of additive manufacturing metals, because the surface finish is often not acceptable for a final part, the critical surface is often a machine. And if that's the case, this type of distortion is really not that big a deal because you machine back to an acceptable state. And the only issue where this would come in would be if there's enough shrinkage that you basically have lost all of your excess material to do the machine. That sort of thing happen. All right, this shows the case to move away from this esoteric silicon carbide, which has many post-processing steps. Let's look and see how it works with distortion in directed energy deposition. Again, this is Tyson's 4, and what's seen here is the build time and the distortion that occurs. This is for a 1-inch thick, 2.5 or 1/10 of an inch thick substrate with a 0.76 millimeter deposition height. So we're basically we're doing big distortion measurements. If there's no preheat, shows this distortion where this is a time plot, and we see that as the build goes on, the distortion actually accumulates, right? So again, we're starting up here at 0 distortion, and so as we move down, in this case with no preheat, we're getting an increasing amount of distortion. Because unlike residual stress, negative is bad, like constant is bad. The distortion we want to be 0, the residual stress we want to be negative. So anyway, by preheating, doing a preheat of the titanium to 400 degrees, not surprisingly, during the build, the distortion, we still get distortion, but we get less of it. All right? So that's the case here. This plot basically shows the more details of how it works at the early stages, the later stages of the build. So this is sort of at the beginning. But if we really build out to the thick layers, this one is a 0.6 millimeter deposition height, here we're 2.54. What happens is we can see that the preheating at some point for really large builds, the preheating actually increases the distortion. So there's a crossover, where for really thick parts we have an increase in distortion. You can see this from the quote I got from the paper. Distortion of thin geometries can be mitigated by increasing the initial substrate temperature. That's shown here. However, preheating of thick substrates can increase the substrate distortion. So we have to be careful about how that works. This is some other work that shows the effect. It turns out that there's an alternate approach to using support structures, and that was demonstrated by the researcher working with DED, again, wire-fed titanium. And what they did is they sort of used a brute force approach where they just clamped down the build plate in a way that so just restricted for moving during the build. So you can see this is a side view. So basically, they have various plates and some washers. So they have the build plate here, but then they built a wall, 10-layer wall, 200 millimeters this way. I'm not sure vertically, but it shows what the dimension vertically is. But basically what they would do is they clamp this wall down, the substrate, they clamp it down to prevent the residual stress from distorting it. And what they found is that by doing so, it resulted in a generation of less distortion in the final part. Again, maybe that's kind of intuitive. But we can see that down here. This is the plot of the deformation. This is 10 millimeters of deformation here. The distortion versus the number of layers during the build. Again, it was a 10-layer part, so they started here, just after the first layer, after the second layer, up to this point, which is after the 10th layer. But what they found is basically they had different scenarios. They had two variables they were looking at. Basically, it's whether they clamped the substrate or not. That was one variable. The other variable was the so-called interlayer cooling time. Because what they would do is they would lay some number of layers, and then they would stop and let everything cool down in the DED. and then they would do another multiple number of layers, wait 30 minutes, and cool down. And the number of layers they picked was either 2 layers, 5 layers, or 10 layers. So effectively, they're basically running so many layers, stopping, waiting 30 minutes, and then going up. And it turns out that also has an impact on the residual spread, on the distortion that occurs. So basically, here's sort of the bottom line. So now I think we can try to interpret this plot. Effectively, what we have here, there are three scenarios where there's basically no distortion. And the 3 of these are wall 1, wall 2, and wall 4, which were all clamped. So the clamping the substrate and to allow it, to prevent it from distorting and moving, actually has a positive effect on the distortion of the DED part. I mean, basically, it kills the distortion altogether. Now, if the substrate is free to distort as the part is filled, then we have these other 3 plots. And it turns out that I think let's see here, the blue one is wall 5, the green one appears to be wall 6, and the purplish one is wall 3. So basically, what we have here is this wall, this distortion, the least distortion in the unclamped specimens is the wall. Let's see, did I do it right? Wall 6, which was let's see, blue is wall 5, is 2. So the blue one, this one here is wall 5 where they pulled every 2 layers. And so it has the most, it has the most distortion. So this is the cooling it down every 2 layers. This intermediate one is 5 layers, and then the 10 layers where basically they didn't cool that at all, they built all 10 layers, and they just let it cool. Actually resulted in the minimum amount of distortion. So again, the cooling effect can have an effect, but obviously the really big effect was whether the wall was clamped or not. Okay, I have a few more slides. I want to talk about oxygen pickup. This is another effect that can happen, and again, it will happen primarily in titanium, but titanium is a very, very popular material. This is a part that has some historical importance. It was done in Texas. Subhan Das built in the late 1990s. He built what we call a high temperature workstation. I'm actually one of the et als on this paper. But what we did is we actually built a metal machine in the mid-90s. Subhan actually designed and built it. This was about 5 years, 6 years before the first commercial metal machine hit the market. And so what we were doing is these were some of the very first parts. I did that first part in a non-commercial material in 1990. This is obviously a commercial material. So it was a missile part. I think we built for the Navy, I think. But it's a so-called sidewinder missile part. And what we had trouble with oxygen. What we see here is the sidewinder specification was the 0.25%. 0.25% oxygen was the maximum allowed. Because I mentioned, I think yesterday, the problem with oxygen in titanium is it lowers the toughness. And again, the oxygen goes in substitutionally, so it's not present in the titanium as an oxide. It's actually dissolved like an alloy element into the metal. And it has a bad effect on toughness, which is the reason that this sidewinder has that 0.25% maximum designation. Which you can see for these various samples that we did SLS hip on, what we see is that we're right up against the limitation, which is not a good thing. However, you know, we can't take the additive manufacturing part, we can't take the total blame for the high oxygen, because the feedstock that we used, which was this prep powder. Prep is plasma rotating electrode something. But basically, I think it's a plasma rotating electrode, and we splat the material. But basically, it makes a very nice spherical powder. But the feedstock itself had 0.19% oxygen. And so we were basically only adding about 0.05 or 0.06 percent of oxygen. So the way that the solution that we did use was to substitute for this prep powder. There's actually a form of titanium 6,4. It's called ELI material. It stands for extra low interstitial, which means the interstitial here is the oxygen. So basically, we got feedstock that had a lower oxygen content, and by running it, we were able to avoid this issue with the oxygen limitation. And I just mentioned here as well that in terms of general, for DED, in terms of just general, the general application, as we work buyer and seller, it turns out that if everyone's okay with reusing feedstock, then it's fine to reuse it. You know, we talked about some issues, I think we did, yeah, with the satellite formation and with increased porosity, some of the factors associated with reusing powder. I guess we talked about that on Monday. But we also can, you know, again, the powder can be sieved, we can remove the satellites, it can be recycled. And again, it's okay to do that, at least according to the standards, if it's okay, if everybody agrees. Having said that, there are a few processing conditions, there are standards under the strictest processing conditions for metal powder where recycling of material is not allowed. And I think part of the reason is the effects of oxygen pickup. Okay, so with that, I guess I'm ready to sort of summarize this part of the talk with the following observations. I think these are the takeaways. One, the PV diagram is really an excellent way to capture the effects of the key, you know, A and B processing parameters on the defect structure of parts. Effectively, it orients us fairly well to what the defect structure is, and if we're producing parts with those defects, it tells us what gives guidance in terms of, do I need to speed up or slow down? Do I need more power or less power? You know, those are very helpful when trying to produce high quality parts. So these PV diagrams really are quite helpful in that regard. As well as, you know, for, as I mentioned on, I guess, Monday, as we try to dial in new materials, it's a great, you know, producing the PV plots, which is what I did with the aluminum powder that I showed on the PV plot. It's a great way to sort of explore that space, and it can be done relatively quickly. The way we can do it quickly is we can build a variety of samples in one build by adjusting the energy source power and the scan speed. You know, those we typically do on the fly with these metal processes. Further, you know, the primary defects are lack of fusion, keyholing, and bowling. These occur again regardless of what the power source is. I haven't seen, as I stand here, I haven't said that, I've seen these PV plots for electron beam extensively, and also for laser beam. I don't know if I've seen any arc processes, but I think they're obviously with the electron beam and the arc, you know, we don't worry about keyholing. You know, it's a laser phenomenon. But we do worry, I would think, at the highest energy levels, eventually we're going to start vaporizing the material and doing other things. But anyway, the third point, metallic feedstock for DED consists principally of rollable and castable metals. Again, if it's rollable and castable, it typically be additively manufactured. And then I give again the sort of classic examples for the different systems. Again, cobalt chrome, again, is a very castable material. The nickel alloys that we showed, the inconels, the models, are all readily processable as well. So, and they appear very well in additive manufacturing. Distortion, it's influenced by the total part height, air cooling, and the amount of damping restraint. That's what we see on these. So we can do some things to try to control distortion, but it still is a very real factor. And then, of course, metal parts can pick up on security processing. Virtually everything except titanium, if you want to do that. I think that would be better than trying to get a head start on the afternoon presentation, which starts, I guess, 2:30. So, is there any comments or questions about what we've been dealing with? Maybe we start a little early. That could be a possibility too. Yeah. Hello.
In the PD course, we have shown fusion defects for titanium and keyhole defects and bar defects for aluminum tensile.
Right.
So, for aluminum tensile alloy, will there be any fusion defects?
Fusion effects on the aluminum alloys. Yeah, I think the answer is yes. Let me go this back up. Yeah, we work with aluminum. But yeah, if I understand your question, I have the right. Where did we go? It was earlier.
Slide number 2.
Oh, maybe I
Slide number 2.
I'm looking for my plot of, oh, maybe I didn't go this way. Let's see if this does it. Here. Yeah, here. Yeah, this is all aluminum that we showed. But so your question was, were there fusion effects like lack of fusion? Yeah. I mean, if we're talking about the fusion errors, yeah, the answer is yes. Yeah, but I mean, we definitely get those. Yeah, they're up here. Yeah, because these are it's like the lack of fusion effects in the aluminum. In this case, yeah, we have to be a little careful. This is pure aluminum, not the aluminum silicon alloy. But the aluminum silicon will do the same thing. We can get these fusion errors, fusion porosity. Absolutely. Yeah. So, yeah.
Any other points? So I have one point, many of the researchers reported they have different mechanical properties with respect to the field directions. But in weave, it's not the optimal conditions what they have fabricated the components.
Yeah.
It should be a uniform mechanical properties in all the directions in weave.
Yeah. Again, I'm going to have to convert. Yeah, I wish my gear was better. Let me try this. Let me see if I can something that maybe might work better here.
Mechanical properties in different orientations.
Yeah. We'll see if we'll see if my iPhone can understand better than I can.
Yeah, mechanical orientations in different different directions will it be common or it is not the optimal conditions what we are getting in just with the wind directions.
Okay, yeah, my echo's not doing any better. Yeah, okay, so, yeah, probably try one more time.
Yeah, different directions in the building.
Different directions.
Yeah,
Yes.
we are getting a different mechanical properties, like slightly variation with respect to
Right.
X or Y or Z. But if they do optimally process conditions, controlling the printing environment, with minimizing the defects and all, are they going to get the uniform in the isotropic?
Yeah, the anisotropic effects.
Yeah.
Try to minimize or eliminate those.
Yes.
Yeah, that's the question.
Yes.
Yeah, okay, yeah, thank you, yeah, sorry for
Yes.
for the delay. Yeah, I have I have two answers for you. The first one is, comes from my background, because I think I mentioned you earlier, although everyone else doesn't know, I did my original doctoral studies in deformation processing. So these were with raw materials. They're worked, deformed plastically in the solid state. And the general feeling is that of all of the manufacturing processes, the highest quality, most reliable processing method is to produce so-called raw metals, or the deformation process. It's sort of the high standard watermark. Other manufacturing processes, like casting processes or additive manufacturing, all typically are less reliable in terms of defect structures and microstructures and performance. And the reason, the way that ties into this question of anisotropy is that if you look at the deformation processing literature, you look at rolling or at raw materials, so the materials that we always compare additive to, the raw metals. If you look at those, the question is, how reliable are the mechanical properties of those materials? Because if we have a given metal, if I do a tension test, I'm not going to get a yield strength of 200 megapascal every single time. There's going to be a scatter. And it turns out that if you look at large numbers of tension tests on lots of material that are raw, they're supposedly identical. It turns out there could be as much as a 10% variation in the mechanicals. And so I always think of this when I look at additive manufactured parts, where they're showing deviations of 5 to 10% in the X, Y, and Z direction. I always think back to these plots that show 3,000 or 4,000 tension down test samples on raw bottoms, where again we're seeing sort of plus or minus 10% variation in the mechanicals. So basically what my first answer is, it's not really, maybe it's not significant. Okay, the second answer though is, there is one place where, actually there are two places where I think the anisotropy can be real. One we talked about, that is with the normal structures that form, the columnar structures, we can get differences in the density of grain boundaries, which means we can get a variation in strength, say, due to Hall edge effects. So in that case, people have done basically it's Z direction testing versus in plane, sort of somewhere in the XY plane testing. We can see differences in the mechanicals for those materials. There's really not a lot that can be done about the grain structure of these parts, other than perhaps doing long-term anneals or high-temperature anneals, try to grow the grains out, and we saw those, here as well. There's also kind of there's a kind of reverse effect that we can do with the grain structure. That is, again, I'm not an expert in this, but I've seen enough talks that I think to be able to sort of communicate the approach. That is the structure of the grain structure that we get during solidification can be driven by two rates. One rate is the rate of grain growth once a particle forms. The other is the rate of nucleation of particles from the melt. So there's a nucleation rate and a growth rate, and depending on how those parts, on how those rates interact with each other, we can produce either a columnar type structure or an equiax structure. And so without being able to give very much detail, it turns out that if you can work those rates and additive correctly, it becomes possible to try and move towards an equiax structure, and we can kind of defeat this columnar rate. At least there's a chance for trying to play that game, and people have done that. You know, this is I think part of the motivation for adding rare earths to the added manufactured parts like scandium and these things. You know, they do it because basically they surface nucleation size, so you can deal with the rates, sort of, you know, that way. But other than that, for greater anisotropy, I think that's really about the best you can do. There is a second type of anisotropy, but it doesn't really apply so much to DED. That is for there were, and I think maybe still are, some systems where we can produce a porous skeleton of metal that is then back infiltrated with something else. And again, if we have a Z distinction in that structure, where we have, say, a high density in the plane, but low density in the Z direction, that can manifest itself in the bottom part after infiltration. But again, I really think that's probably not much of a The big one is the particles. This is the columnar orientation. And again, really, basically what you have to do is you have to destroy the cell. And it's the way I would do it would be high temperatures for a long time would be the easiest way to do it, just break it out. So, but then of course that may have its own penalty too, right? So there you go. So anyway, yeah. I guess, yeah, I guess we're fairly close to the end of the time. Maybe it's okay with you, so we can go ahead and dismiss, have lunch, and take an extra 5 minutes for lunch. And we're back here at 2:30.
Yes.
Right, 2:30. No, we'll start case studies, which will be